In section 7.2, we formulate the channel coding theorem. The channel coding theorem consists of two parts. The direct part says that information can be communicated through a DMC with an arbitrarily small probability of error at any rate less than the channel capacity. The converse says that if information is communicated through a DMC at a rate higher than the capacity, then the probability of error is bounded away from zero. Here is the definition of a channel code. An NM code for a discrete memoryless channel with input alphabet X and output alphabet Y is defined by an encoding function f from the index set 1, 2 up to m to alphabet x to the power n, and a decoding function g from the alphabet y to the power n to the index set 1, 2 up to m. In this definition, n is called the block length of the code. The indices 1, 2 up to m are called messages, and a set of messages, denoted by W, is called the message set. The sequences F1, F2 up to Fm are called code words, and a set of all code words are called the codebook. In a channel code with block length n, the encoding function maps a message to a code word of length n, and the code word is sent through the channel. Upon receiving a sequence of length n at the output of the channel, the decoding function maps the sequence to a message in the message set. Here are some assumptions and notations. We assume that W, the message, is randomly chosen from the message set W, so that the entropy of the message W is equal to log of m, where m is the size of the message set. We use bold x to denote the vector x1, x2 up to xn, the transmitted sequence, and bold y to denote the vector y1, y2 up to yn, the received sequence. Thus, bold x is equal to f of w. That is, the transmitted sequence is the code word of the chosen message. Let w hat equal g of the received sequence y be the estimate on the message w by the decoder. We now discuss a few performance measures of the channel code. For all messages w from 1 up to m, let lambda sub w be the probability that the decoded message is not equal to w, given that w was the chosen message. And this is equal to summation, the probability that the received sequence is y, given that the transmitted sequence is the wth code word, and the summation is over all y sequence such that g of the y sequence is not equal to w. That is, the summation is over all y sequences that are not decoded to the message w. Lambda w is called the conditional probability of error, given that the message is w. The maximal probability of error of an NM code is defined as lambda max, which is the maximum of all lambda w's. In other words, lambda max is the conditional probability of error of the worst code word. The average probability of error of an NM code is defined as PE equals the probability that w hat, which is the decoded message, is not equal to w, the chosen message. we are going to see how the average probability of error is related to lambda max. Consider PE equals the probability that W hat is not equal to W. This can be written as the summation over all message W, the probability that the chosen message is small w, times the probability that W hat is not equal to W, given that the chosen message is small w. Now the probability that the chosen message is small w is equal to 1 over m, and the probability that W hat is not equal to W, that is a decoding error occurs, given that the chosen message is small w, is equal to the probability that the decoded message is not equal to small w, given that small w is the chosen message. And this is just equal to lambda w by definition. Therefore, we see that PE, the average probability of error, is actually the average over all lambda w's. Therefore, PE, which is the average of all lambda w's, is less than or equal to the maximum of all the lambda w's, which by definition is equal to lambda max. That is, PE is always less than or equal to lambda max. The rate of an NM channel code is 1 over n times log m in bits per use. Recall that n is the block length of the code and m is the size of the message set. Here, all the logarithms are in the base 2. A rate R is asymptotically achievable for a discrete memoryless channel if for any epsilon greater than 0, there exists for sufficiently large n an NM code such that 1 over n times log m, that is the actual rate of the code, is greater than R minus epsilon, and lambda max is less than epsilon. That is, the rate of the code is arbitrarily close to R, and at the same time, lambda max is arbitrarily small. Theorem 7.15 is the channel coding theorem, which says that a rate R is achievable for a discrete memoryless channel if and only if R is less than or equal to C, the capacity of the channel. This is the main theorem of this chapter.